And this session, which is dedicated to test methods, is going to be started by a presentation from Manuela Battipede. I hope I said that right, Manuela. Ciao. And some of her colleagues who are coming from the Politecnico di Torino, which is a wonderful city. It's a long time since I went to Turin, but it's always a wonderful place to visit. Like some of our colleagues, Manuela has prepared a pre-recorded presentation, which I'll be playing for you in a few minutes. But she and her co-authors are available to answer our questions at the end of their pre-recorded presentation. So as before, please take advantage of the chat function to send those questions in. I'll just remind you that this presentation or these proceedings as a whole are being recorded, and you should bear that in mind if you write something or say something or show something on the screen, that your comments may well be recorded. There are several members of the team, but I'll just introduce Manuela, who I think in the start of her presentation goes on to introduce her colleagues. Manuela is an associate professor at the Politecnico di Torino, but she's a long-time fan of the institution because that's where she got her PhD in 2000. And she has a great deal of skill and experience, which we can see through the fact that she's got more than 100 journal and paper publications over the course of her career, working with a lot of different research institutions in Europe and in the USA. And at the moment, she is fully recognized by the European Communion as one of their experts, in actual fact, for these technical subjects. She's a flight test engineer, which is why she's here to talk to us today, working on the certification of changes to civil aircraft and rotorcraft. As she mentioned, CS23, 27, and 29. And at the moment, I believe she's also working with Copter as a CVE. So she's got a lot of activities to keep her time filled. It's amazing, Manuela, that you found the time to write a presentation and join us today. So thank you very much for that.
My pleasure.
Okay, I'll set up the video and get it playing, and then we'll come back to you and your colleagues for questions at the end.
Good afternoon to everyone. Before starting the presentation, I would like to give a brief introduction of the team. I represent today the Flight Test Department of TPS, which is the Italian DOA, in charge of the certification of the STC that we will introduce in a minute. Raffaele Di Caprio represents EASA and was involved as the flight expert of the EASA certification team. Manfred Blair is our flight test pilot, and Matteo Azzola is the HTO of TPS. A couple of years ago, a request was made to TPS by a helicopter operator to certify the external installation of one or two baskets on the AS350 series, including B1, B2, B3, and B3E. The baskets are meant to increase the payload volume capacity to carry bulky payloads such as the Bambi bucket or luggage or medical equipment. Each of the two baskets can be positioned on the helicopter skid with an upward opening and can be mounted in an asymmetrical configuration, a right or a left single basket, or in a symmetrical configuration, which is the configuration that we call dual basket. According to EASA Part 21, this modification is considered a major change, which implies that a certain number of flight requirements, among the others, need to be reassessed. Back in 2019, to support the industry, EASA issued a certification memorandum on external installation on helicopters, which provides specific guidance for certification of external installation that are considered non-extensive and for which paragraph 865 of the CS is not applicable. Paragraph 865 is specific for external loads, such as those carried in oyster or sling operations, which are covered by a dedicated memorandum. The memorandum on external installation on helicopters indicates flight testing as the ultimate mean of showing of compliance with the affected requirements, and endorses practical approaches which have proven to be effective and consistent with the consolidated guidance material. As we all know, this material is not binding, but it generally consider a relevant support for the applicant, as it contains a great extent of practical indication derived from valuable lessons learned. For example, a sound approach encouraged by the memorandum to show compliance with the performance requirements is to perform tests on both the unmodified or baseline and modified configuration. This method is known as a back-to-back approach, and of course some points of the flight envelope are expected to be more affected by the modification embodiment than others, and it is crucial that the comparison is made at the maximum and the most critical configuration of the envelope. The baskets are not massive, but what was clearly identified as affecting the performance, for example, was an increase in drag and lift, of course, which could be more detrimental at higher forward speed. Worst case scenario for performance was then identified in dual basket or symmetrical configuration because it involved a greater increase in drag. Extensive technical consultation among the parties involved in the certification program was dedicated to a specific paragraph of the memorandum, which indicate that HV diagram investigation must be performed to show compliance with requirement 71. Flight test investigation of the HV curve, if executed as indicated by the reference guide materials, involve certain numbers of auto-rotation landings from low speed, low altitude initial points that even in the most conservative build-out approach involve a substantial risk. However, from the initial investigation of the certification program, paragraph 71 was identified as potentially affected by the change, and TPS came up with this alternative procedure in the effort of reducing risks and costs associated to the test. EASA saw that the method had potentials and accepted to evaluate it. So we started a two-phase testing campaign, and the evaluation of this alternative procedure presented today is the result of the joint effort and professional skills of the whole team. In detail, HV curve verification implies testing whether, in case of a sudden power loss and within certain limits of altitude and speed, the rotor maintains enough power to enter out rotation in a forward descending trajectory, which precedes the flare and landing. That, of course, must be performed maintaining vertical and forward speeds within acceptable limits. In more detail, in case of a power loss, the rotor torque is suddenly reduced, causing a rotor speed K, and the maneuver to enter out rotation consists in a quick reduction of the collective pitch. And in fact, by reducing the blade pitch, the rotor drag can be reduced, and the resultant of the aerodynamic forces can rotate to propel the blade and increase the rotor speed. The use of the cyclic control counteracts the helicopter tendency to pitch up and down, depending on the position of the center of gravity. And we can see that in steady out rotation, a given value of the collective pitch will cause the helicopter to settle on a unique descent speed. The pilot can control the rotor speed using the collective pitch, meaning that the lower the pitch, the higher is the rotor speed. But in practice, the usable range of rotor speed is very restricted. If the rotor speed is too low, for example, the blade will stall and lose lift. If it increases over the prescribed upper limit, the loads on the rotor hub and blades roots could exceed the structural limits. So the safe range is typically within 80% to 120% of the nominal power on rotor speed. This is for transient excursions, and between 90 to 110% for the stabilized condition. So it was decided to start with the preliminary analysis that had to be supported by the test results obtained in the first part of the test campaign, which did not involve any HV curve testing. The preliminary analysis consisted in analyzing the dynamics of the out-rotation maneuver and identify whether the embodiment of the change could have had an impact on any of the basis phases in which the maneuver can be split. So before entering into the details, we can start analyzing the avoidance zone Z, which is defined by 4 points. There is point D on top, that is at 0 airspeed, and at that minimum height for which the potential energy can still be converted into kinetic energy to accomplish steady descent in auto-rotation and, of course, a safe landing. From this point of view, it is not easy to understand whether the modification could have an impact or not, but we will see that this one is one of the key points that must be analyzed. Point C is also known as the knee point, is the most critical point in the HV curve as it involves a very low ground height combined with a rotorcraft speed for which the additional drag generated by the basket could have surely been detected. Points A and B are a very low ground height, and for this combination of height and speed, it was estimated that the presence of the basket was irrelevant, if not beneficial, because the baskets were offering a wider resistance to phase, which could have contributed to reduce the helicopter speed. So as we mentioned already, the key point of the proposed alternative procedure for showing of compliance with requirement 79 is to investigate the out-rotation dynamics to assess whether the embodiment of the external installation can have an impact on any of the phases that here we have sketched. The overing, which is an extreme condition for which an engine failure can occur. Then there is the out-rotation entry, which is the phase immediately after the engine failure and the pilot reaction. Then there is the glide, which is not a steady regime analyzed in performance assessment, but it is the transient which goes from the engine failure to the steady regime for which the helicopter is descending at the minimum rate of descent, considering that, of course, the engine failure can occur from any initial condition in terms of forward speed from 0 to 50 knots, and this is for the AS350. Next phase is flare, and then we have the touchdown. So the first phase, we say, is the overing, and it was estimated that the embodiment of the basket implied, of course, an increase in drag with helicopter speed above a minimum value. In point D, or eye overing, however, this effect is not detectable because there is zero speed. Chances were, however, to find a difference in the power required to maintain the over condition, as the presence of the basket could have had an effect on the induced velocity distribution and then on the dynamics which precede the entrance in auto-rotation. This effect was expected to be proportional to the percentage of the rotor area affected by the basket blockage, which was roughly estimated around 1.5%, which is surely a very small amount. The over condition, however, was indicated as a critical condition and had to be investigated. The big key parameters that must be analyzed in this phase is the auto-ground effect overing performance in terms of the power necessary to hover, which is measured through the torque level in relation to the helicopter weight that must be converted in a generalized weight to facilitate the back-to-back approach. The analysis is completed then by the estimation of the in-ground effect overing performance, which can also give good indication of the impact of the change in the proximity of the lower hovering point. The second phase is the auto-rotation entry, and we all know that without sufficient power to maintain the hover, for example, the helicopter will descend, and the descending aircraft can use the relative upward flowing air to drive the main rotor, and this is the essence of the auto-rotation. More details: in case of power loss, the rotor torque will be reduced, causing rotor speed decay. And the initial rotor speed decay rate can be estimated by the ratio of the unbalanced torque due to the engine stop and the rotor inertia. The scientific literature report that the factors affecting the rotor speed decay are, besides the rotor inertia, the rotor speed and the torque at the instant of the power loss, as well as the ratio of the thrust required over the maximum thrust that the helicopter can produce. Important additional factors include also how quick the pilot is in attempting to contain the rotor speed within the limits, with the maximum acceptable delay time defined as the delay that causes the rotor speed to reach the minimum power of transient value before rising to achieve a stable auto-rotation condition. The key parameter for the evaluation of the impact of the change is then the rotor speed time variation immediately after the maneuver performed by the pilot to enter the auto-rotation as a consequence of a power loss. The third phase is the glide, and after a power loss in hovering that is considered as the extreme starting point, the key characteristic here is the ability of the helicopter to accelerate to a rotor speed of a rotorcraft speed corresponding to the minimum rate of descent, which is approximately equal to the speed of maximum rate of climb Vy. To evaluate the acceleration characteristics in this phase, measurements must be focused on the loss of altitude, delta H, and the time required to accelerate in this unsteady glide the rotorcraft from 0 to the flare speed Vy. The first phase is flare, which is assessed in a qualitative way in terms of the effectiveness of the control to flare the helicopter to decelerate drastically to a forward speed compatible with a safe touchdown. A great extent of the first part of the flight test campaign was thus dedicated to gather data that could give qualitative evidence in support of the proposed procedure. So specific tests were planned and performed to investigate the 4 phases already mentioned: hovering in-ground effect and out-of-ground effect, auto-rotation entry, glide, and flare. The objective of the hovering performance test was to determine the power required to hover out-of-ground effect at different gross weight, with particular relevance for the maximum takeoff weight, and over performance tests were executed with the free over flight technique, with the helicopter gross mass in a range from the maximum takeoff mass of 2,250 kilograms to 1,822 kilograms. And quick variation in weight was made possible by removing bags of ballast for each test point, and in the end by removing crew members. The test for auto-rotation entering consisted in a set of maneuvers to enter auto-rotation, starting from the hover condition. To perform this test, the lead flight test engineer initiated a simulated engine failure by retarding rapidly the fuel control lever to a ground idle position. We used a 1 second delay from the initiated power loss to the control actuation. And following this 1 second delay, the collective was lower and rotor speed decay was monitored and video recorded. Upon reaching a forward speed in the range of 50 to 55 knots, the outer rotation was recovered by adding engine power through the fuel control level. This procedure was repeated multiple times for each configuration as to obtain results with statistical meaningful. In all the configurations, as we can see, the outer rotation minimum rotor speed is never reached, and outer rotation is stabilized within 8 to 9 seconds from the engine stop. As we mentioned already, the glide immediately after the engine failure is that transient regime which is necessary to reach the speed of minimum rate of descent, which is approximately Vy. Tests were conducted at multiple altitudes and initial conditions, and results reveal that the behavior of the helicopter in both the modified configuration is acceptable. There is, of course, a slight difference in the altitude drop, and in fact, we can see that the modified configuration reaches the target speed after higher altitude drops, and this can be related to the extra drag introduced by the baskets. And in fact, the dual basket configuration in this respect perform a bit worse than the single basket configuration. Differences in the transient dynamics, however, are in the order of 5% in terms of altitude loss, which goes unnoticeable in the economy of the Bull maneuver. Last part of the results concerned flight characteristics, which were investigated, as we already say, in a qualitative way. And tests were conducted at low altitude, performing quick stop maneuvers at different speeds and flare angles for the three configuration. Pilot commented that there was no noticeable differences in the effort requested to flare the helicopter. To conclude, the proposed procedure allows considerable reduction of test points, which implies a reduction of costs in flight testing without any reduction in the safety margin. On the contrary, safety is announced as in the case that it is at the end shown that necessary, only affected and relevant part of the HV curve will require actual verification. In particular, there are a few major benefits for this procedure. First is that no complete engine out landing were conducted, especially in the proximity of the HV curve. Second is that all testing involved engine failure simulation can be performed at safe height above terrain, since there is no more requirements to demonstrate full out-rotation landing starting from specific high and speed points as for the full HV curve demonstration. And just to give a quantitative estimation, it has been estimated that less than 30 points were needed, opposed to the foreseen 80 or more test points necessary for a complete investigation of the HV curve, which is usually performed at the maximum take-off mass involving at least 2 density altitude, so means finding a low and high altitude field and using a proper build-up approach in speed and height. This concludes our presentation. I just want to express my gratitude and appreciation to the ASA team involved in this certification investigation, especially to the flight expert for the patient support it gave both to ideas and people. Thank you.
Very good. So hopefully you could all hear that that presentation okay. I certainly could on my side. I had nobody writing in on the comments to say that they were struggling to hear, so I guess it must have been good. Thank you, Manuela, for sharing that with us. I know you recorded that presentation quite recently, and from what I could tell, you had a lot of people who were trying to get to your house or office to join you. We could tell from the noise in the background, so it's a very popular subject. There are no questions on the chat, but I had a couple of questions myself which have come in, and I can see that we've got colleagues from IESA who may be able to answer directly to this question as well. Is there a chance that the work you have done on this subject and the results that you've had from this trial could potentially lead to a reduction in the formal requirements in the certification specification, so that we may have a more officialized way that it's okay to reduce the amount of test points we're doing?
Good afternoon to everyone. I'm very pleased to answer this question. First of all, we are together with other colleagues in EASA. We are thinking to include this test method as an acceptable means of compliance for verification of HVD diagram in the CERT memo that Manuela was mentioning in the presentation. So it's first of all one thing that is going to become public as an acceptable method to demonstrate this. We think that this new method has a lot of benefits, not only in terms of safety and economy of the flight test, but also in terms of costs for small DOAs that are involved in installation for rotorcraft. Regarding the certification specification itself, I think it's not the requirement itself that should be changed, not because of this flight test method. However, there are discussions in place also with the FAA colleagues regarding the applicability nowadays of the HV diagram requirements and how this should be demonstrated, and the meaning of the HV diagram, because the way it has been done in the past and until nowadays, the HV diagram is somehow been misinterpreted by a lot of operational pilots.
Okay, thank you, Raffaele, for that answer. I don't know, Manuela, did you want to add anything to that, or?
Oh, I think I've said anything. I mean, I just want to, it was a long thought, something related to what was presented yesterday. I mean, just a very, very simple modification with a long test campaign. So it was long, but it was an added value. And so I'm very happy that, you know, we are almost close to closing the FTC.
Okay, well, that actually links into my second question. As you say, this example which you presented was not a very complicated modification with these baskets. Do you see that there could be any limitation to how far you could go in terms of the size of modification to the helicopter and still apply the same method, or could it in theory be scaled to any modification?
Well, this is something, I mean, you can go through this procedure and you just analyze the result and you see whether you can like just reduce the HV curve verification or if you can skip it completely. So this is something that you can use for whatever modification, and then results needs to be analyzed to see whether you can stop or go ahead.
Okay, great. Well, thank you for those answers to those questions. There is nothing more on the chat. Oh, Raffaele, did you want to add something to those comments?
No, actually, no. Manuel answered pretty well.
Okay. Well, in that case, I thank you very much for taking the time to prepare your presentation and the paper. I probably haven't mentioned yet, but all of the papers will be published afterwards and made available, I guess, via our website, but we'll let you know how that's going to be done. So thank you again for taking the time and for your presentation.